Welcome to those of you who are new to this type of homework, and welcome back to those of you who got introduced to this last year. I want to remind you at this point that you need to get your notebook, and the other thing that you want to have handy, you pull it over here, your calculator. So get those. You can stop this and get your notebook if you haven't already got it there. Things we're going to talk about today. Well, this first unit we're going to do in 4 sections, radian and degree measure. I'm going to take my time with that to make sure that we get the right foundation under us before we get into the trig functions themselves. A lot of this is a review of your geometry, but we're going to learn some new ways of looking at angles. At least I think it may be new. Placing an angle into standard position, really, it's so simple. All it means is that your vertex is right here, your initial ray is here, and your terminal ray is somewhere on the coordinate plane, emanating from the origin. Measure angles in either degrees, which you are very familiar with, or radians, which you may or may not have been introduced to. They make a whole lot of sense, and we absolutely need them when we're doing certain kinds of measurements with angles. We'll talk about why later. Complementary and supplementary angles, well, you remember that. Complementary angles, for both of these, we're talking about pairs. Complementary, a pair of angles that add up to 90 degrees, and supplementary are a pair of angles that add up to 180. So we'll do a little work with that. Just make sure everybody's up to speed. Given the central angle, we know that would be something, let me change my color here. That would be an angle that's maybe lying here. Given the central angle, and when we talk about a central angle, do you remember from geometry? We're always talking about a circle. So we're talking about this angle. If we know the central angle and we know the radius, find the arc length. In order to find the arc length, we are definitely going to define that central angle in radians. And then finally, in the last 2 sections, we're going to be working on word problems which are about travel along a circular arc. It turns out that that's a very common problem that we have to solve. Because, for example, building roads, most of the time there's, at least here in New England, you find quite a few curves. Okay, how is an angle formed? Let's take a ray here. We've got one. Locate its endpoint. So the endpoint is the part that doesn't have an arrow on it. You can rotate this ray about its endpoint, and let's try doing that. So we can go, it looks like a clock. Can go all the way around, and we get all different angles this way. If I rotate all the way around, what would you tell me? I've made one full rotation. One full rotation. Let's try it again. One full rotation. What would you call one full rotation? I'm listening. That's right. In one full rotation, how many degrees have I traveled? $180, somebody's saying? No. How many degrees have I traveled? 180 would take me halfway around the circle. In a full rotation, oh, okay, most of you were saying that, 360 degrees. You can stop anywhere you like, you just get a different degree. The end position with its starting position form the angle. The end points of the rays is the vertex. I'm just getting that vocabulary back. Let's face it, it's been a while since you looked at geometry. Standard position for an angle. We keep the vertex at the origin. Standard position, by the way, always requires that you use a coordinate plane, an x-axis and a y-axis. We're going to refer to the measure of this angle as theta. This is a Greek letter. Perhaps you've encountered it already in science. If I want to show a positive angle, I'm going to rotate oh, wait a second here. Unlock. Sorry about this. I'm going to try ungrouping here too. Grouping. All right, I'm going to go back. I have to, I thought I was so ready. Well, I'm not. I was trying to rotate this like I did before. I'm going to do this actually with my pen this time. We have our initial side right here. If I want to describe a positive angle, I'm going to move counterclockwise. Counterclockwise, exactly the opposite of the way a clock moves its hands. And that will be counterclockwise. That will be a positive angle. If I want to describe a negative angle, I move clockwise. I start at that initial side and move down. This will be a negative angle. And this is moving clockwise. Now let's look at some of the definitions of angles. You know all of these. We'll draw them in. An acute angle. Do you remember the definition? It's any angle that is less than 90 degrees, right? So this would be an acute angle, and it would be positive. A positive acute angle. I could have drawn a negative acute angle. Here's a right angle, and of course a right angle is exactly, that is a terrible looking straight line. And I could do this curved line here. We typically indicate that we've got a right angle by drawing that little box. So remember that. In this case, I drew a positive right angle. I could have drawn negative. An obtuse angle. Well, we did acute, which is between 0 and 90 degrees angle measure. We did right, which is exactly 90 degrees. And obtuse, as you remember, is greater than 90 degrees and up to 180. So if I do a positive obtuse angle, There it is. How about a straight angle? Straight angle is exactly, whoo, I did really good that time. Exactly 180 degrees. So let's go back here. In this case, your angle, and we'll call it theta, is greater than 0 and less than 90 degrees. A right angle, theta, is equal to 90 degrees. For an obtuse angle, theta is greater than 90 degrees, less than 180 degrees. And for a straight angle, okay. Complementary angles, let's just draw some examples of complementary angles. What do they have to add up to? They have to add up to 90 degrees. So I could have this angle here and this angle here. Since they add up to 90 degrees, they're considered complementary. For supplementary, they add up to 180. So if I had this angle here and this angle, I would have supplementary angles. One of the things you should notice here, unless the supplementary angles are both right angles, 90 plus 90, you're always going to have one obtuse and one acute. Coterminal angles. Oh, this is a good thing to talk about. Suppose I have this angle here, which looks to me, let's say it's 45. And one of the things you better be careful of, my drawings are not necessarily precise, but we're going to say this one is 45 degrees. All right. And over here, I'm going to say that this angle is, now don't be blown away by this, let's hope I get my math right, 405 degrees. Anybody have any idea how I get that? It looks exactly the same as my 45-degree angle. So let's try it. I go all the way around for 360, and then I add that remaining 45. So these are actually different angle measures, very different, aren't they? But they are called coterminal for, I think, pretty conspicuous reason. Their terminal sides are identical. We could do other things with these as well. Let me show you another one, which is a little more interesting perhaps. I could go, from my initial side, I could go negative. And what would that? That would be negative 315 degrees. We're going to talk a lot more about negative angles coming up. But notice that when I just look at the initial side and the terminal side, they look identical when you've got coterminal angles. We do have a problem here. We're going to face it very soon. The input variable in any trig function is an angle measure. We have up to this point always measured our angles in degrees, or for some of you, usually measured our angles in degrees. Degrees have no relationship to linear, do they? If I tell you that we've got a 45-degree angle that doesn't tell us anything about the length of the rays, or if we're drawing a circle, I should say the radius of that circle. In a trig function, we've got an input, which is an angle measure, and an output, which is a real number. We need a unit of measure for angles that relates to the length. Oops, that's not going to show up there. The length dimensions of circles, so that I can talk about the circumference, I can talk about the radius. It's going to be very important. So one thing with a circle, what defines a circle? Its center and the length of its radius. So if we can use this radius to help us out, that would be most useful, wouldn't it? I'm going to say that we're going to start out figuring out how to measure what would we call the half revolution of a circle. Call it a semicircle, and how many degrees does it have? 180 degrees. But now I want to measure it in terms of a length, and I'm going to use the radius, the length of the radius, as my way of measuring my angle. Now it's going to change. It's not going to be called a radius anymore. I'm going to call it a radian. So radian. This length is going to be then curved. We see it here. There's one. If I took this radius and curved it, this is exactly one radius in length once I've curved it, and I'm going to call it 1 radian. My second radius, I haven't quite got to a half a circle or a semicircle yet. I'm looking to get to 180 degrees. I've got 2 radians. So let's put another one on here. Here's my third radian, and now I'm almost there. So just a little bit more than 3 radians will define 180 degrees, or a half a circle. How much more do I put on here? This little piece here is less than 1. So halfway around a circle is 3.1416, going on and on and on. Thank you. There's a few of you thinking or talking about this. Yes, but that is pi. So how many radii does it take for me to get halfway around a circle? Pi radian. Okay. How many radians are in 90 degrees then? If it's pi radians to do 180, and I'm talking about 90, what's this angle measure in radians? It's not pi, it's half of pi. How many degrees are in a third of pi? A third of pi radians. 1/3 pi radians. So that looks something like this. Pi over 3. Yeah? What is it? It's 1/3 of 180, isn't it? pi radians is 180 degrees, so 1/3 of pi radians will be 1/3 of 180. Okay, so let's use this now. We're going to find the length of an arc intercepted by a central angle. So we're talking about a circle with a radius of 5 inches, and the central angle is half a radian. Well, we know 1 radian would be right here, wouldn't it? And what would the arc length of 1 radian be? Exactly equal to the length of the radius. So 1 radian, if I went around, 1 radian would be 5 inches. So if I go a half a radian, it's going to be 2.5 inches. Find the radian measure of a central angle that intercepts an arc of length S in a circle of radius R. Oh, no numbers? Okay, let's see if we can use the same thinking and figure this one out. I'm going to draw my circle up here. Okay, we have radius R, and we have an arc length of S. It's a weird looking S, but we know what it is. And I want to find this measure. Notice when we're dealing with arc length, we're always talking about radian measure. Degrees will not work. So I know my answer is not going to have number, well, it may have a number, but it's not going to have a number value for me. How did I find it over here? The arc length was 2.5, and I found that because, let me see, my radian measure on this one, I should change colors. Whoops, that's fancy pen. Let's go to blue. Okay, my radian measure on this one was 0.1, right? Half a radian. So, I mean 0.5. 0.5 radians. My radius was 5. And how did I find my arc length? As long as I had this in radians, I could find my arc length this way. It's quite simple. The radius times the radian measure of the central angle. So why wouldn't this formula still work for me here? Find the radian measure of a central angle. So it's going to be radian measure equals arc length divided by radius. That's supposed to be an R. This could be a very handy formula. Okay, let me take a look at the answer I figured out last summer. That's right. This is a very handy formula. We're going to use this. In almost every lesson, we're going to have an example that we work through. This is work that you should have completed in your notebook. You don't have to do it along with me. You can shut me down right now and then go ahead and do it and then come back and check your answers. 180 degrees. Well, let's move backwards for a moment. Might be useful for us to grab this. Copy. You've got it in your notes probably. But, oops, I see even a better one right here. I'll copy this one. Copy. And we'll just have this beside us for reference. All right. 180 degrees is pi radian. So that makes it easy for me to write this, doesn't it? I'll do my answers in green. 180 degrees is the same as pi radians, and how many revolutions around a circle is that? Yes. 30 degrees. Well, let's see. 30 degrees, if we said 180 divided by 30, that would go in 6 times. So 30 degrees is 1/6 of pi. So we're going to say pi over 6. And how many revolutions will that be? A half a revolution would take us 180 degrees, and we're only going to go 1/6 of that. So we've got 1/6 of, remember, of means multiply, of 1/2 of a revolution. What do we do when we're multiplying fractions? We multiply the numerators together. So that would be 1/12 of a revolution. Now the next example has us converting 2 degrees from radians. We should be able to do that. Pi divided by 2 is 180 degrees divided by 2, so we know what that is, 90 degrees. How many revolutions will that be? Well, this is half a revolution. I'm only going half of a half, so it's, that's right. Now suppose I do 3/4 of pi radians. Well, 4/4 of pi radians takes me to right here. So 3/4 of pi radians is going to take me right about here. How am I going to figure this out? Well, 3/4 pi is going to be equivalent to 3/4 of 180 degrees. Now it turns out 4 will go into 180 evenly, won't it? How many times will 4 go into 180? Well, I'll go in twice, that'd be 90, so 45 degrees. So we're saying that 3/4 of pi is the same as 3 times this. What is 3 times 45? I hope I got that right. 135 degrees, is that what you got? 135. If it isn't, you'll of course tell me in class tomorrow and we'll straighten this out. How many revolutions have I made if instead of going, oh, I said it wrong earlier, 4/4 of pi would take me all the way over to here. 2/4 of pi takes me here, and 3/4 of pi takes me here. So how many revolutions? Well, not a half a revolution, but 3/4 of a half revolution, right? So 3/8 of a revolution. You are going to know this stuff inside out. It's going to help you so much going forward. Spending a little more time on this with your class than I have in my previous classes. I think I skipped through this too quickly. It's so important to be able to move from degrees to radians to revolutions and back. So now we're at revolutions. If you've only gone 1/8 of the way around a circle, we could figure this one out pretty easily, couldn't we? We know how many degrees are in a circle. Let's think about it that way. We've got 360 degrees in a circle, and we're going 1/8 of the way. How many times will 8 go into this? Is that right? 45 degrees? So we've got 45 degrees, and 45 degrees is 1/2 of a right angle, so it's 1/4 of pi radians, right? So it'll be pi divided by 4. Believe me, in a few weeks these will come to you so quickly. Oh, here's an interesting one, 2/3. We haven't thought about thirds. Let me get rid of this. We can think about it exactly the same way we just did the other one. 2/3 of our way around 360. So 2/3 of a full revolution. That's 360 degrees. And that will become 2 times 3 goes into 360. Yeah, 120, right? Did I get that right? Two-thirds of a full revolution, and that's all over 1 now. So it's 240 degrees. That's an interesting one. That takes us beyond. So instead of all of these were less than half. So all of these were semicircles, way up to here. And now we go beyond half a revolution, which takes us over into this quadrant here. So 240 degrees. Okay, so how many radians will that be? If 180 is pi radians, then 240 is how much more? Okay, I think you've got it. Four pi over 3. Would that be right? Well, if we look at this ratio, we could divide both of these by 60, so that would reduce to 4 over 3. So that's the proportion we've got here. And we can use that with pi because we are checking against 180, which is equal to pi. Okay. The next one, we've got 225 degrees. So we're going greater than a semicircle, going greater than the 180. That's greater than 1 pi, isn't it? 1 pi is 180. So well, how much greater is it? 225 degrees. What's the ratio here? Well, I think I can I divide both of these by 45 degrees? Is that going to work? 45 will go into this 4 times, correct? And 45 will go into this 5 times. So the ratio that we have between 225 and 180 degrees is 5/4. So it would be 5 pi over 4. 5 pi over 4. Does that make sense? Sure it does. We knew that 4 pi over 4 would take us right to here. And we had to go further to get beyond 180 degrees. How many revolutions is that? How many revolutions? Well, it's less than 1 revolution, isn't it? Well, we could look at it this way. 225 degrees compared to 360. It's going to be some fraction of 360. What fraction of 360 is this going to be? 5/8. 5/8. So this, like the one above it, has been greater than a half a revolution. It's taken us into the next quadrant. Okay, we're still practicing. Let's try this one. We know what we've got for radians. Let's figure out what we've got for degrees. If we've got 5/3 pi for radians, that's going to be 5/3 of 180 degrees. And that will become 60. So it'll be equal to 300 degrees. Does that make sense to us? Let's write it down and think about it for just a minute. 3/3 of pi would take us halfway around the circle. That would be pi radians. So 5/3 has got to take us quite a ways. So yes, that does make sense. And how many revolutions, or what portion of a revolution will that be? 5/6. We're starting to see some relationships building here. Oh. Now, just when I think I'm starting to get it, look what we're going to have. 11/15. Oh. 11/15 of a revolution. Well, let's start by figuring out how many degrees that is. It's fairly simple. We just say, okay, it's 11/15 of 360 degrees. And 15 will go into that evenly. What will that be? 15 going into that. Well, let me think about it this way. If I were dividing 360 by 30 degrees, it would be 12. So this is twice as many, so it's got to be 24. Somebody check me on that and make sure I'm okay. Is that right? 24 times 12 will give me 360. Well, let's verify that. Turn my calculator on. 24 times 15. Yeah, okay, so I just verified my calculation there. Now 11 times 24, oh, as long as I got the calculator, let's let the calculator do the work. 24 times 11. Calculators are great for doing these arithmetic problems for us. 264. All right, and 11/15, can you figure out what that is going to be in radians? Well, you may have noticed there's a relationship here. 5/3 pi, 5/6. 5/4 pi, 5/8. 4/3 4/6, right? This is equal to 4/6. I mean, we wouldn't actually write it that way. I'm just doing it so that I can help you perhaps see the relationship here. 1/4 is the same as 1/8, 3/4, 3/8, 1/2, 1/4. What's happening? We can always double the denominator, right? Well, in this case, that doesn't work so well. But what is this equal to? 22 over 30. True? Does that help us at all? So how many radians do you think we're going to have here? If you use the same numerator and divide the denominator by 2, you get how many radians, don't you? So 22 pi divided by 15. 1 radian. Ha 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 ha. So the first one where we don't see pi in there. And that can throw us off when we get accustomed to always seeing pi. By the way, I want your answers, when possible, to be expressed in pi radians. This, of course, would be an exception to that. But usually our answer will be expressed in pi radians. It's a lot easier to understand. So how many degrees in 1 radian? Well, let's write it out. If pi radians equals 180 degrees, 1 radian is going to equal what? How can we figure this out? 1 radian. Well, let's look at this as what as a number. Usually we don't use the decimal, but 1.1416. So 1 it's about 1/3, isn't it? It's about 1/3 of 180. And we know that just from looking at this. It's a little less than 1/3, isn't it? So let's see what we get. 1/3 of 180, of course, we know it's 60. Let me pull my calculator up again because that might be useful here. I don't want to do this in my head. So we're going to say, turn your calculator on, 180 degrees divided by 3, well, wait a second. Delete, go back, yeah, delete that. Divided by, why don't I just use pi since it's available to me here, it'd be a little easier. Right? 180 degrees divided by pi, and that's going to tell us how many degrees are in 1 radian. That might be a useful thing to know. So it's 57 point, let me pull that up again so we can look at it. Let's call it 0.3. Push this out of the way, that'll work better for me. 0.3. And how many revolutions will that be? This is tricky, isn't it? How many revolutions will that be? Well, it'll be 57.2 2958 of 360. That'll be how many revolutions it is. Again, I think I'd be better off if I pulled over a calculator here. Let me divide this by 360, and that will tell me how much of a full revolution I have here. It's going to be 0.1592. So it'd be 0.1592. Now, if I thought that might be a nice even fraction, maybe I'd prefer to write it that way. How could I check that? Go to Math, Fraction. You've maybe done this before. And see if you come out with anything. No, it's just going to be that lousy decimal. Finally, pi revolutions. This exercise is getting us to think about a lot. Okay. Pi revolutions. So that's pi revolutions. That's 3.1416 revolutions. How many degrees is that going to be? Well, it's going to be 360 plus 360. There's one revolution. There's two revolutions. Let's put another one over here. 3 revolutions. So it's going to be something more than this. Oh, we're definitely going to get our calculator out for this. So we've got 1 revolution, which is equal to 360 degrees. But we're not going 1 revolution, we're going pi revolutions times, and with our calculator we'll simply use the pi. How many degrees is that going to be? Yikes. That's a lot of degrees. Let's call it, we'll round to the nearest degree. 1131. 1131. 1131 degrees. What's the matter with me? I didn't put degrees on here. That's sloppy. I wouldn't accept that from you. All right. Now we're going to see how many radians is that. Oh boy. How many radians is that? Well, 1 pi radian is 180. So if we've got 1131 degrees and 180 is 1 pi, if I divide that out, I'm going to know how many pi radians I have. So I've got the number right here. Let's use it. We'll divide by 180. 6.28. Well, that's kind of interesting, isn't it? Looks like 2 pi, doesn't it? Let's try that. 2 times pi. Maybe you already saw that. Right, it's 2 pi. Well, of course it's 2 pi. We've seen that again and again and again, that the number of revolutions is always twice the number of pi radians. Yes, what a good exercise. So some of you just skip to the end to check your answers. Now, back in class, when I see you tomorrow, we're going to do the homework assignment number 1. I'll also answer any questions that you had out of this session. Looking forward to seeing you tomorrow.